Hello, I'm Jim Tung, and it's my honor to deliver the keynote talk at this year's MATLAB Virtual Conference. The title of my talk is Embracing Complexity. And you may be wondering, why is it that someone from MathWorks is talking about embracing complexity? After all, our MATLAB and Simulink products have a proven ability to make the complex simpler. Being able to take the content from a 1970 Stanford PhD thesis on advanced control with thousands of lines of Fortran code and reducing it to 8 lines of executable MATLAB code. Taking the cost, time, and complexity of developing physical prototypes in developing systems and control algorithms, enabling engineers to work with models to explore many more variations much more simply. And so why am I talking about embracing complexity? It's because the task of making the complex simpler isn't so we can just solve simple tasks. It's to enable us to tackle even more complex challenges. Recently, a professor, Rajkumar from Carnegie Mellon University and his associates put forth a series of possible grand challenges for engineering. And let me go through a few of them. The goal of 0 automotive traffic fatalities, minimizing injuries, and having significantly reduced traffic congestion and delays. Blackout-free electricity generation and distribution. Perpetual life assistance for people who are too busy, who are older, or disabled. Energy-aware buildings. And being able to provide world-class medicine wherever someone is based and where they're located. These are some of the grand challenges that I believe are why we must embrace complexity. But how do we get there? How do we get to embracing complexity? Well, we must break it down. And so let's start with what people do today, which is to manage complexity. If we look at today's automobile, much has been written up in the press and among engineers about the number of ECUs, control units in today's car, 50, 60, 70 processors. But we sometimes lose sight of the functions themselves that those processors perform. Engine management, transmission management, chassis control, different types of active safety systems, things that provide body electronics that enable performance of certain power functions in the chassis. Driver infotainment systems as well. Let's take a look at an adaptive cruise control system, a system that detects when a vehicle ahead of the vehicle slows down or is stopped, and it then commands the vehicle to slow down or stop accordingly to avoid a collision. That's functionality that's enabled through today's microcontrollers and DSP systems. But it isn't a single function. In fact, if you look at what's inside of an adaptive cruise control system, it must integrate with the engine management system, as well as the electronic stability system, often called the ESP, and the braking system as well. Those different functions must be networked, must communicate in order to safely perform the adaptive cruise control function. In order to support the management of that level of complexity, the automotive industry has defined a standard platform for collaboration called AUTOSAR. AUTOSAR is an architecture that enables different vendors, different suppliers to provide different kinds of functions and enables those functions to communicate with each other to enable the composition of more complex functionality as shown in the adaptive cruise control situation. MathWorks provides tools for modeling and simulating the behavior of those algorithms, and so we provide functionality to deliver components that fit into such an AUTOSAR architecture. Let's look at a completely different situation, though. Neuroimaging of brain activity. This has its own type of complexity. There are different ways of getting data about the brain activity. Some quite old, PET, EEG, MEG. some more recent, functional MRI and SPEC. Each one of these uses a different set of techniques for looking at brain activity in different sections of the brain. Because of the techniques, they may have differences in how they're able to resolve spatial activities, how they're able to resolve activities in a temporal manner as well. Some are more expensive, and so therefore are not able, there's less data that's available from those methods and modalities. Some are cheaper, but perhaps have lower resolution. So being able to take data from all those different modalities and combine them together is something that neuroscientists really need to be able to understand brain activity. One of the challenges, though, is that those measurements come from different kinds of people. Perhaps the same person at different stages of life, or different people at different times and different settings. And the brain functions, the parts of the brains themselves, are based in slightly different locations from individual to individual. So there's the need to correlate and to register that information across the individuals to enable larger scale analysis. The researchers who are doing this work in neuroimaging are asking themselves different questions. What is the function of a certain portion of the brain? How does a change in the structure of the brain affect activity? How does one part of the brain connect to another and activate its activities? And the researchers who are doing this work are located all around the world. To help bring this community together, to help manage these different levels and types of complexity, a platform was created. SPM, which stands for Statistical Parametric Mapping, is several things. First of all, it's a set of techniques that enable the disparate types of data sets from the different modalities, from different subjects, to come together, to be correlated and reconciled. It is also a software package. SPM is a tool that was written in MATLAB starting about 20 years ago and continuing today. It supports the different modalities that I showed in the previous slide, and it enables neuroscientists to look at different data sets, combine them, and apply analysis techniques to look at what parts of the brain are active, either during a certain set of activities or when the person is learning something, but also looking at some of the neurological consequences of different pathologies, different diseases, and brain injuries. Because SPM is written in MATLAB, researchers from around the world are able to add their own techniques to SPM. Those are techniques such as utilities for dealing with data sets and cleaning up bad data. They could be the result of one person's doctoral thesis, where they want to share it with the broader community to see if it inspires other ideas and collaborations. And it also brings subsets of that community together, subsets who may be interested in a specific topic, such as what is the cause of Alzheimer's disease, and what are some possible ways of detecting it early and slowing its progress. Late last year, the Neuroimaging journal did a survey of the publications in the neuroscience and neuroimaging area. And one of the questions they asked is, which software packages do you use as a scientist? What are the tools that are used as the foundation for some of those papers? And as this chart shows, SPM was by far and away the most frequently used software package in the neuroimaging community. That popularity has enabled the rapid dissemination of some of the newer techniques in neuroimaging. The base technique in SPM is general linear modeling, the technique that's used to register the different information from different data sets so the statistical techniques can be robustly applied on different samples. But as the modalities have evolved, the analysis techniques have also evolved. And so SPM also includes techniques for time series analysis, taking advantage of some of the dynamics that techniques such as functional MRI can capture and then can be analyzed. Some of the newer techniques, such as dynamic causal modeling, enable researchers to look at brain connectivity questions. For example, does region A affect region B so that it's responsible for activation of certain functions? What is the connection that is modulated by something such as attention Structural changes to the brain can be analyzed through techniques such as voxel-based morphometry, the ability to look at structural changes, either in one person over years or across individuals, that enable the researchers to look at phenomena such as aging or pathologies such as dementia. It's also critical as scientists are studying neurological diseases such as Alzheimer's and Parkinson's. Another technique for managing complexity is modeling and simulation. Being able to abstract the engineer or the scientist away from the details to be able to look at the problem at a higher level of abstraction, to understand it, to analyze it, and perhaps to revise an idea for how to deal with it. If we look at modeling and simulation, it's a well-adopted set of techniques, but it's used in different ways in different situations. If I follow the thread of just one area, looking at energy systems and looking at sustainability, let's see how modeling and simulation is used. In the classroom, it may be used to teach an engineering student some of the core concepts of a system, such as a microgrid system. It hides the details of the specific components. It enables the student to understand structurally how the system is composed, to play what-if scenarios based on different configurations and different scenarios. It's also important that the models can be simulated. In this case, looking at a wind turbine system, being able to look at the different parts of the system, the mechanical, the electrical, the control algorithms, seeing how they interact, seeing how they affect each other in such a mechatronic system, and being able to visualize them as shown here in the new version of SimMechanics. The MathWorks platforms for modeling and simulating both enable this kind of modeling description, but they're also mathematically very rigorous and extensible. And that permits modeling and simulation to be used not only for teaching, but also for research. In this case, a call for papers for a competition that's actually taking place right now. It's the third year of this competition, looking at different aspects of fault detection in a wind turbine and wind farm system, and looking for ways of designing fault-tolerant control of the wind turbines in that system. In this case, modeling and simulation is both to describe and to simulate and to understand, but also to drive new research activities and move forward the state of the art. The same modeling and simulation capabilities also used in industry. Hydro-Quebec models wind power plant performance, running simulations in real time, enabling them to anticipate when equipment changes and maintenance are needed. TransPower helps to ensure the reliability of New Zealand's national grid by constantly evaluating the amount of reserve power that's available in the case of some degradation or damage to portions of the grid. They do that by simulating the entire grid, including the generators, the loads, and the various components every 30 minutes. At the MATLAB Virtual Conference, you can hear more about how TransPower does this by looking at track 3, where they'll be giving a talk. And Horizon Wind Energy develops revenue forecasting and risk management models for how to place and when to place wind farms. In this case, looking at it from a financial standpoint. They're able to integrate that simulation capability with their entire IT infrastructure and enables them to manage risk, which saves them millions of dollars. Beyond modeling and simulation, to analyze, to understand, and to do research on systems, models also enable automation, another way of managing complexity. In this particular case, automation of certain development tasks in a process. For example, being able to automate the simulations of a design in order to optimize that design. At Docomo's labs in Beijing, China, they build system-level simulators to look at different kinds of protocols for their different communication systems. These are massive simulations of massive models, incorporating different network layouts, channel models, modulation orders, channel coding rates, interference levels. And they want to be able to optimize their systems so that they take into account different kinds of configurations that might involve dozens of base stations with hundreds of devices. In building their models and running their simulations in an automated way, they're able to cut their development time significantly and are able to explore many more scenarios and verify and optimize their designs in those situations. Another aspect of automation is automatic code generation. The MathWorks products for code generation are very widely used and very mature in their uses. A diverse set of uses, from performing trade studies, doing rapid prototyping, generating the code that goes into the embedded system, or generating models that will be then used to run in a hardware-in-the-loop simulation for testing. The code can be generated to target different types of devices, from microcontrollers to DSPs to FPGAs and to PLCs, as shown in this example with this Festo robot arm. And the application of code generation can range anywhere from student projects to deployment on production systems to certified applications, such as this case from Eurocopter. Another case of automation is newer, automatic test vector generation. The ability to look at the design and to automatically generate the test cases that will cover the design, that will exercise all the different aspects of the design. This is particularly useful when the designs get more complex, and it's very difficult and time-consuming to manually generate those tests. Today in Track 3, you'll hear a talk from General Motors, their HVAC team, who use Simulink Design Verifier to automatically generate the test vectors to exercise their designs. And so far, in talking about managing complexity, I've talked about three things: having a platform for collaboration, for modeling and simulation, and for automating different development tasks. And at MathWorks, we place a strong focus on ensuring that MATLAB and Simulink are very good platforms for those capabilities. When our users bring those capabilities together and apply them in their processes, what do they get? What they get is agility. I'm not talking about agility in terms of agile methodologies and development processes. I'm talking about the capability, the ability to respond quickly to changes that you may encounter. Let's take a look at how Lear Corporation, an automotive supplier, has achieved agility.
These days we have to work very fast. We get into situations where the customers come in on a Friday with a need to change to a spec. We work around the clock with our teams, so we make the changes to the models on this side in the US, and we pass them along to the engineers, say, in India, and they're able to take them and run with them and do their validation.
We had one product in particular where the timing of the project was extremely short. A typical automotive electronics product can take anywhere from 2 to 3 years for development. For this particular product, we were able to turn the product around from quoting and award to full volume production in 100 days.
Going from 2 to 3 years for product development to 100 days, that's significant. And so we've looked at various approaches for managing complexity: collaboration, modeling and simulation, automation, and agility. And this is the state of the art today in industry. It is also reaching down into academia, where schools are changing their curriculum, changing their activities in order to build a stronger engineering foundation that leverage these capabilities. Through competitions in different areas: automotive, robotics, and systems biology. Through project-based learning and incorporating that into courses. Through scientific studies that take observations from real-world experiences, real-world situations, in order to perform complex data analysis on them. From innovative courses, such as this one in India, that takes a multidisciplinary engineering view to the topics. But today there's an opportunity to reach even earlier, to build the foundations in even younger students. And that opportunity is afforded through some of the technology that's now available. For example, kits that enable students, youngsters, to build complex systems, smart systems, very easily from these types of toolkits. Inexpensive processors such as the Arduino, very powerful, very inexpensive. And embedded software that's needed to perform the algorithms in order to make those systems smart. But we believe that embedded software knowledge should not be a prerequisite for being able to explore these types of smart systems. And so in the latest version of Simulink, in both the professional version and the student version, we've added the ability to connect Simulink to the hardware, ignore the software, and immediately run algorithms on the target device by simply choosing to run on the target hardware from the Simulink menu. If you want to learn more about this capability, it's described further in the virtual conference in Track 4, Exploring MATLAB and Simulink in Academia. And so we've talked about various ways of managing complexity, but that is not enough. We need to embrace complexity. I go back to these grand challenges. These cannot be done with today's embedded systems. These cannot be done with today's smart systems. But the embedded systems are their ancestors. And the smart systems today are really the first generation of the systems that will accomplish these grand challenges. It's timely to think about these grand challenges today because they are not feasible today, but we can start to see how they will be feasible. I talked earlier about the diagnostic power of neuroimaging. But let's think instead about therapeutics. What if we were able to take a cancer cell and to move it closer together to other cancer cells to make it easier to radiate them and to deal with the treatment of cancer? What if we were to be able to take a very small particle and deliver a solution to a genetic disorder or a solution to some other physiological issue at a very, very small scale? The scale we're talking about is very small. We're not talking even about microns. We're talking in some cases about something significantly smaller. Things that are down around the spectrum of visible light. Two particular things are interesting here. Being able to manipulate the position of cells, which might be the level of microns, or being able to move quantum dots, very, very small nanoscale particles that are able to diagnose phenomena and in fact deliver treatments on those phenomena. At the scale we're talking about, being able to control the motion of these types of particles, these sizes of particles, is very difficult. Laser tweezers are considered the state of the art, but in fact they are too large and consume too much energy to manipulate quantum dots. So a group at the University of Maryland is looking at treating this issue in a different way. Controlling the particles by controlling the fluid that the particles are in. Using techniques for electroosmotic flow control to be able to use electrodes and electric fields to manipulate the charged particles in the fluid and thereby move the particles in that fluid in a very controlled, very precise manner. This experimental setup that's shown here shows how the red dot, which could be a quantum dot, can be moved in one direction with high precision. The red blood cell, to the above right, can be moved in a very different direction, even though it's very close to the quantum dot. And the yellow nanowire can be moved in yet a third direction, all by manipulating the control of the flow. Let's take a look at this in action. The cell in the middle of the screen is being controlled in its motion. The red dot is the command position, where the operator wants the cell to go. And the blue dot is the exact position at the time. the cell is being moved because the flow, the fluid that the cell is in, is being moved as well. And so the researchers at Maryland are trying to understand how easy is it to move these types of cells? How much resistance can they overcome if they encounter another cell, such as the one to the right, with its set of microtentacles? What is the ability, what is the force that they can generate through this type of technique? Looking at an even smaller scale, they're trying to understand how to control quantum dots, perhaps 10 nanometers in diameter, and trying to understand how to move them along a controlled path, again using this nanoscale flow control. The quantum dot is shown in that highlight, which alternates between square and triangle, and is showing the actual position of the quantum dot as it's being moved along the letters. Another broad trend that illustrates this need to embrace complexity is cyber-physical systems. What are cyber-physical systems? If I look at Wikipedia, part of the definition is that it's a system featuring a tight combination of and coordination between the system's computational and physical elements. If I were to read that, I could look at today's embedded systems and see how they would fit that definition. But if I read further down in the definition of Wikipedia, it says, unlike more traditional embedded systems, a full-fledged cyber-physical system is typically designed as a network of interacting elements with physical input and output, not as standalone devices. And so these are devices that are in a network. They may be connected to each other. They may not be connected to each other. And so I tend to think of cyber-physical systems as collaborating systems of systems. Really an evolution, a large evolution from today's embedded systems, smart systems, and systems of systems. What does it take to make cyber-physical systems happen? A group of researchers from industry, academia, and government have started to put together a concept map for what comprises cyber-physical systems. It includes models that include discrete time, continuous time, discrete event, and so on. Human in loop is important, including all of the non-deterministic aspects of the human in the loop, but also bringing into account then the fact that the human has to see things. So what are the perceptual and cognitive aspects of the model? These models must be multiform in time. That is, they each operate in time, but they don't necessarily have a global clock. They each have their own sense of what the time is. Another aspect is control. Adaptive control, predictive control, robust control. However, there's also the need to enhance the control techniques to take into account communication and network, and perhaps failures of networks. Another aspect is the communication itself, the concurrency, and how these systems optionally interoperate. That involves new models of computation, an understanding of how real-time systems work, how they compose, and how they decompose. Another aspect for these types of cyber-physical systems is the need to understand when they are right. How do you verify them? How do you validate them? Can they be done analytically? Can they be done through simulation or some combination of both? There are many other aspects that make up cyber-physical systems as well, including how do you build wireless actuators? How do you deal with protection of the system from outside influences and infiltration? But cyber-physical systems have applications in many different areas, as shown here. One aspect of cyber-physical systems, these collaborating systems of systems, is to make each of the systems smarter. Here's a video of a modified Audi TTS vehicle driving along a racetrack in the hills in California. What's complex about this system? What makes this system smart? It's the fact that this vehicle is driving itself. This is an autonomous vehicle that's moving at about speeds of 150 miles per hour along the test track. Now, the group that's doing this work doesn't have the objective to create autonomous race cars. Instead, they want to look at racing and at race drivers to try and understand what are the techniques to get as much capability of the vehicle applied to the maneuver that you want to perform. Because they believe that understanding that better will enable them to create safer cars. Professor Chris Gerdes puts it this way: we want to use every bit of the car's capability to be as safe as possible. We want to develop autonomous vehicles that can avoid any accident that is physically possible to avoid. And so while a lot of autonomous vehicle work is focused on scene building, being able to look at paths that are conservative to get from point A to point B, this group is looking at a different aspect of the problem. What if the vehicle encounters a patch of ice? What if the vehicle encounters brake fade or has bad tires? What is its ability to recover from that situation? In order to do that, the group started by looking at the mathematics of racing lines, the optimal line around a race curve, breaking it down to the line segments and arcs, just as a race driver would. And they've been able to take many tens of thousands of measurement points and reduce them to a small set of segments that enable the automobile, in this case using XPC target, to maneuver quickly around the race course. But they learned that drivers also take advantage of other aspects of the vehicle, including drift, countersteering, steering with the throttle. And so they've built autonomous vehicles that can perform those types of activities as well. And now the group is looking at another aspect of the system, which is the driver. They have connected electrodes to the driver's head to be able to take EEG measurements as the driver is taking the car around the race course, to try and understand when are they having high brain activity and when are they doing things instinctually. This video shows a driver taking a move around a curve, a set of curves, where they have to exert a lot of mental energy, as shown with that red bar in the right. But interestingly, the researchers also found that when the driver is going around a corner and the back end of the car comes loose, the driver can react very quickly, as you just saw there, without a lot of additional brain activity. So they're trying to understand what are the cues that the driver gets that causes them to take those reactions. Can they capture them? Can they model them? Can they implement them? And can they help the addition of those instincts into the autonomous vehicles to make the vehicles safer? It's not simply about single autonomous vehicles, because we're again talking about networked systems. And so we move on to autonomous traffic management. Take a situation where a vehicle has adaptive cruise control. What are the options if there's another vehicle ahead of that first vehicle that also has adaptive cruise control? What is their ability to share information so that they can work in a more reasonable and efficient manner? Can the system be designed so it's robust when other vehicles, such as the one highlighted in red, are not similarly equipped? These types of systems of collaboration and of non-collaboration are difficult to design, but very important to design and to verify correctly. A lot of the activity in cyber-physical systems is focused in these types of issues. Here's a shot taken from a paper that was delivered on threat assessment. When two cars come from the left and from the right of this picture, and the car on the left has to swerve to avoid a pedestrian, what are the options for that car to get back into its lane before colliding with the car coming from the right? What are the abilities for those vehicles to react in an appropriate time? In this case, the work is done in MATLAB, and in fact, it's worth noting that much of the work in cyber-physical systems is done with MATLAB and Simulink, which we're very proud to support. A lot of the research in cyber-physical systems are trying to understand this whole set of issues that are associated with cyber-physical systems. One simple test bed that helps to expose some of those issues is this one. It's a robot system that moves parts from one place to another. You can think of it as an industrial automation pick-and-place robot. You can think of it as a proxy for cars in lanes of a highway. The gantry system itself has a camera that points downward, so it can see where the blocks are located and what colors they are. The gantry itself can move from left to right in order to move those blocks from place to place. However, we're not simply talking about a gantry system for a set of cargo. We're talking about a network of interacting elements. Each piece of cargo, in fact, has its own set of characteristics and properties, requests about what it wants to do and what it is able to do to get there. For example, the blue block has a desired position in the end to want to be on the bottom of the stack. It is able to move in a certain way, and it wants to have the highest priority in this collaborative system. Well, if we think about this text, we can describe it, in fact, as a state flow chart. And if we look at the other blocks as well, they may have different properties, different requests, different priorities, each of which can be captured in state flow charts. And once you've done that, you can start to look at how you can design that system of systems. How will the robot arm communicate with the different payloads? Take account of their ability to act in certain ways and their prioritizations? And is it able to get, at the end of a process, into a configuration where the three blocks, in this case, are stacked in the configuration and the order that is desired? Well, this may seem like a toy problem and a toy example, but the complexity comes alive when we start to ask some of the questions about this test bed. For example, what instructions will ensure that the desired result will be achieved in all scenarios, even if more payloads are added? What instructions provide the optimal performance across those different scenarios? Is the system robust to lags in communication in networks or computation within the devices? How much synchronization is required? And can the performance of the system be validated and verified? Simulink is used as one of the tools for people doing research in cyber-physical systems. And the example that's shown here is available from the MATLAB Central file exchange area for you to download and to learn yourself about cyber-physical systems. As you attend this MATLAB virtual conference, you have different roles, different responsibilities, different interests. You may be a student who's interested in acquiring the skills or gaining the motivation to pursue an engineering or science degree and career. You may be a teacher who's helping the student and motivating the student along that path. You may be a researcher who's trying to create and define some of these breakthrough concepts, whether in the neurosciences, cyber-physical systems, or elsewhere. You could be a development team that's looking to add more functionality to the products that you already ship today. Or you may be an industry or a consortium of companies that is looking to position yourselves longer term to be better equipped to take care of the challenges of tomorrow. Regardless of who you are and what your interests are, there should be something at the virtual conference for you today. We'll tell you more about the tools for modeling and simulation, ways that you can collaborate using MATLAB and Simulink, some of the automated capabilities for code generation, text vector generation, and so on. Capabilities that will enable you to become more agile today. And I hope you find value in that information. But in the back of your mind, I would like you to also be thinking, as you walk through this conference and attend the materials, what will you need to embrace complexity? Enjoy the conference.